In this lecture, we shall study fluid dynamics. Fluid dynamics is a sub-discipline of fluid mechanics that deals with fluid flow in motion. There are many branches in fluid dynamics, aerodynamics and hydrodynamics, few among the popularly known fluid mechanics. It involves in a wide range of applications such as calculating force and moments, determining the mass flow rate of petroleum through pipelines, predicting weather patterns, understanding nebula in interstellar space, and modeling fission weapon detonation. Fluid dynamics is the study of the movement of fluids, including their interactions as two fluids come into contact with each other. In this context, the term fluid refers to either liquid or gases. It is a macroscopic statistical approach to analyzing these interactions at a large scale, viewing the fluids as a continuum of matter and generally ignoring the fact that the liquid or gas is composed of individual atoms. Fluid dynamics is one of the two main branches of fluid mechanics, with the other branch being fluid statics, the study of fluids at rest. Every discipline involves concepts that are crucial to understanding how it operates. Here are some of the main ones that you will come across when trying to understand fluid dynamics. Basic fluid principles. The fluid concepts that apply in fluid statics also come into play when studying fluid that is in motion. Pretty much the earlier concept in fluid mechanics is that of buoyancy, discovered in ancient Greece by Archimedes. As fluids flow, the density and pressure of the fluids are also crucial to understanding how they will interact. The viscosity determines how transient the liquid fluid is to change, so is also essential in studying the movement of the liquid. Here are some of the variables that come in this analysis. Basic viscosity. This is denoted by mu. Um, Another quantity is density. It is denoted by rho. And kinematic viscosity. It is denoted by nu, and which is the ratio of mu and rho. Now, what is a flow? Since fluid dynamics involves the study of the motion of fluid, one of the first concepts that must be understood is how physicists quantify that movement. The term that physicists use to describe the physical properties of the movement of fluid is flow. Flow describes a wide range of fluid movement, such as blowing through the air, flowing through a pipe, or running along a surface. The flow of a fluid is classified in a variety of different ways based upon the various properties of the flow. For example, steady versus unsteady flow. What is steady flow? If the movement of fluid does not change over time, it is considered a steady flow. This is determined by a situation where all properties of the flow remain constant with respect to time. Or alternately, can be talked about by saying that the time derivatives of the flow field vanish. A steady state flow is even less time dependent because all of the fluid properties remain constant at every point within the fluid. So if you had a steady flow but the properties of the fluid itself change at some point, then you would have a steady flow that is not a steady state flow. All steady state flows are examples of steady flows. A current flowing at a constant rate through a straight pipe would be an example of a steady state flow and also a steady flow. If the flow itself has properties that change over time, then it is called an unsteady flow or a transient flow. As a general rule, steady flows make for easier problems to deal with than unsteady flows, which is what one would expect given that the time dependent changes to the flow don't have to be taken into account, and things that change over time are typically going to make things more complicated. Another classification is laminar flow versus turbulent flow. A smooth flow of liquid is said to have laminar flow. Flow that contains seemingly chaotic, nonlinear motion is said to have turbulent flow. By definition, a turbulent flow is a type of unsteady flow. Both types of flows may contain eddies, vortices, and various types of recirculation. Though the more of such behaviors that exist, the more likely the flow is to be classified as turbulent. The distinction between whether a flow is laminar or turbulent is usually related to the Reynolds number. The Reynolds number was first calculated in 1951 by physicist George Gabriel Stokes, but it is named after the 19th century scientist Reynolds. The Reynolds number is dependent not only on the specifics of the fluid itself, but also on the conditions of its flow, derived as the ratio of inertial forces to viscous forces. Another classification of fluids is compressible versus incompressible fluids. Gases are generally treated as compressible fluids because the volume that contains them can be reduced. An air duct can be reduced by half the size and still carry the same amount of gas at the same rate. Even as the gas flows through the air duct, some regions will have higher densities than other regions. As a general rule, being incompressible means that the density of any region of the fluid does not change as a function of time as it moves through the flow. Liquids can also be compressed, of course, but there is more of a limitation on the amount of compression that can be made. For this reason, liquids are typically modeled as if they were incompressible. Now we discuss about applications of fluid dynamics. Two-thirds of the Earth's surface is water and the planet is surrounded by layers of atmosphere. So we are literally surrounded at all times by fluids, almost always in motion. Thinking about it for a bit, this makes it pretty obvious that there would be a lot of interactions of moving fluids for us to study and understand scientifically. That's where fluid dynamics comes in, of course. So there is no shortage of fields that apply concepts from fluid dynamics. This list is not at all exhaustive, but provides a good overview of ways in which fluid dynamics show up in the study of physics across a range of specializations. For example, oceanography, meteorology, and climate science. It has applications in aeronautics, geology, and geophysics. Hematology and hemodynamics. The biological study of blood includes the study of its circulation through blood vessels, and the blood circulation can be modeled using the methods of fluid dynamics. It has applications in plasma physics and astrophysics and cosmology. Even the principles of fluid dynamics can be applied to do some analysis of traffic analysis in communication systems. Now we shall study a very important equation. This is known as continuity equation. Okay, to derive this continuity equation, we consider a pipe like this. Okay, so the area of cross section of this uh, is A1, and the velocity of the fluid flow is V1 here, and in time delta t, the fluid moves a distance, we call it delta x1. Okay, our time is delta t. Okay, here the exit point, this is entrance point and this is exit point. The velocity is v2, area of cross section is a2, and in time delta t, the fluid moves this distance delta x2. Now continuity equation represents that the product of cross sectional area uh, of the pipe and the fluid speed at any point along the pipe is always constant. This product is equal to the volume flow per second, or simply the flow rate. So the flow rate, if we denote it by capital R, which is area of cross section A and the speed of the fluid flow, and this is constant. A is the area of cross section of the pipe. Through which the fluid is flowing, and V is the speed of the fluid flow. Okay, so this is flow rate R, and this is constant for a fluid flow through a pipe. Okay, now we consider some assumptions of the continuity equation. First, we consider that the tube is having a single entry and single exit, as we have shown here. A single entry point here, single entry and single exit. Second, we assume that the fluid flow in the tube is non-viscous. So the viscosity is 0, for example. Non-viscous. Third, we assume that the flow is incompressible. That means the density of the fluid is constant in time. Incompressible. density is constant. And fourth, the fluid flow is steady. Okay, with these assumptions, now we are going to find the continuity equation. Let us consider the fluid flows for a short interval of time, as I have shown there. In time delta t, the fluid moves a distance delta x1 with velocity v1 here, and the cross section of the pipe or tube at the entry point is a1, and similarly in this delta t time, the fluid at the exit point, just before exit point, moves the distance delta x2, where the velocity of the fluid is v2. So at this time, uh, at the time delta t covered by the fluid, the distance covered by the fluid is delta x1, distance equal to velocity speed into time. At the entry point, the speed is v1 and time is delta t. So at the entry point, that means the lower end of the pipe, the volume of the fluid that will flow into the pipe in time. This is actually, instead of at, we should say in time. This is better. Fluid in time delta t is v equal to the area of cross section into the distance delta x1, which is a1, and delta x1 is v1 delta t. It is known that mass is the product of the density and the volume. So the mass of the fluid in delta x region will be delta m1 equal to density into volume. So rho is the density. Okay, let us see rho 1 at the entry point, but actually we shall later on will take that the density of the fluid is constant. So at the exit point, if the density is rho 2, we will assume that then rho 1 equal to rho 2. For the moment, let us take the density of the fluid at the entry point is rho 1 and the volume v. So rho 1 a1 v1 delta t. Therefore, the mass flux is delta m1 by delta t equal to rho 1 a1 v1. Let us say this is equation 1. Similarly, the mass flux at the exit point, that means at the upper end, is delta m2 by delta t, and which will be rho 2 a2 v2. In this, the density of the fluid between the lower end of the pipe and the upper end of the pipe remains the same. So since the flow is incompressible, rho 1 equal to rho 2 equal to rho. So the mass flux at the lower end of the pipe must be equal to the mass flux at the upper end of the pipe. Now using equation 1, 2 and 3, we have rho a1 v1 equal to rho a2 v2, or a1 v1 equal to a2 v2. So you see this is constant. The product of the area of cross section and the speed is constant. If capital R is the volume flow rate, then this equation can be written as R equal to A into B, which is constant. This is the continuity equation. Okay, next we shall consider Bernoulli equation. Bernoulli's principle formulated by Daniel Bernoulli states that as the speed of a moving fluid increases, the pressure within the fluid decreases. Although Bernoulli deduced this law, it was Leonhard Euler who derived Bernoulli's equation in its usual form in the year 1752. The Bernoulli principle states that the total mechanical energy of the moving fluid comprising the gravitational potential energy of the elevation, the energy associated with the fluid pressure, and the kinetic energy of the fluid motion. Remains constant. Okay, if you read it again, the total mechanical energy of the moving fluid comprising the gravitational potential energy of the elevation, the energy associated with the fluid pressure, and the kinetic energy of the fluid motion remains constant. And mathematically, you can write P plus half rho V square plus rho GH equal to constant. Where P is the pressure of the fluid, V is the velocity of the fluid, Rho is the density of the fluid. And H is the height of the container. Bernoulli's equation gives a great insight into the balance between pressure, velocity, and elevation. Now we shall derive the Bernoulli equation. Okay, here we shall consider a pipe. Let us say the velocity here v1 and velocity here v2, pressure is p2, pressure is p1, and area of cross section is a1. Here area of cross section is a2. Now we have some assumptions. This elevation is y1. This is the axis of the tube, and here this is y2. Now the assumptions. The density of the incompressible fluid remains constant. So the fluid is incompressible. And another assumption is energy of the fluid is conserved as there are no viscous forces in the fluid. There are no viscous forces. Okay, so these two assumptions we have. Now first we apply the energy conservation in the form of work kinetic energy theorem. And this is the work done is the change in kinetic energy. Now what is delta K? change in kinetic energy. This is K2 kinetic energy at the exit point. This is here, and K1 is here, kinetic energy. So K2 minus K1, and this one is 1/2 M2 V2 square minus 1/2 M1 V1 square. Now we have M1 equal to M2 equal to M, or we call it delta M. So we call it delta M, and which is equal to density into volume. So we can write down is 1/2 M, and this is V2 square minus V1 square, half rho delta V and V2 square minus V1 square. So this is our delta K. Now the work done on the system arises from two sources. The work system arises from two sources. We have Wg, which is the work done by the gravitational force. Okay, work done by the gravitational force, and which is minus delta mg, and this is y2 minus y1, which is minus rho into delta v g and y2 minus y1. Okay, if this is equation 2, okay, this is equation 2, and this is 3, and this is 1. Okay, now we have another source of the work done. Okay, first let us discuss why the negative sign is here. The work is negative here because the upward displacement and the downward gravitational force have opposite directions. Okay, so this work done on this system arises from two sources. This is the one source, the work done by the gravitational force, and the other source is The other source of work is from the pressure. Work must also be done on the system at the input end to push forward the fluid that is located ahead of the emerging fluid. In general, the work done by a force of magnitude F acting on a fluid sample contained in a tube of area capital A to move the fluid through a distance delta x is this is the work done on the system at the input end, and this is because of the pressure is P into A. This is the force and delta x, and this one we can write down small p and here A into delta x, but this is volume, so is P into delta V. The work done on this system is then P1. So at the entry point, pressure force is then P1 and delta V, and work done and the work done by this system is minus P2 into delta V, which is at the exit point. P2 into delta V. This is negative because this is the work done by the system, and this is work done by the pressure force on the system. And therefore the work done by the pressure is then we'll have to add these two, P1 delta V minus P2 delta V. Okay, this is equation 4. Now if we use equations 2 to 4 into equation 1, we get W. Okay, W equal to delta K. This is the total work done, and this is the sum of Wg and Wp, which is delta K, and Wg is minus rho G delta V, and Y2 minus Y1, and this is P1 minus P2 into delta V, which is equal to half rho delta V into V2 square minus V1 square. From this we can write down, we cancel delta V from both sides, and this one rho G y2 minus y1, and this is minus p2 minus p1 equal to half rho v2 square minus v1 square. This one can be written as p1 plus half rho v1 square plus rho g y1 equal to p2 plus half rho v2 square plus rho g y2. And this equation means that p1 plus half rho v1 square, so at the entry point you see the sum of pressure and this term is equal to at the exit point. That means we can say that P pressure half rho V square plus rho G Y equal to constant, and instead of Y, if we say this is H height equal to constant. This is the Bernoulli equation. There are a lot of applications of this equation, and we shall solve some problem at the part 3 of this chapter by applying this formula. Okay, this is for today. In the next lecture we shall discuss about viscosity, coefficient of viscosity, and we shall discuss about drag force and Stokes law, and also terminal speed of a body moving through a viscous fluid.